At the very edge of our understanding lies a hidden layer of reality, one where the smooth fabric of space-time dissolves into a turbulent sea of energy. This isn't science fiction. It's the quantum foam, a dizzying frenzy of virtual particles popping in and out of existence so fast they defy the laws of physics as we know them. What if this chaotic microscopic realm holds clues to the birth of the cosmos itself? For decades, scientists have grappled with the idea that beneath the calm surface of our universe, space itself might be seething with activity, a theory that could rewrite our origin story. Today, we're peering into this enigmatic frontier where the rules of gravity and quantum mechanics collide, where black holes might leave traces in the void, and where the first sparks of existence could still flicker. This is the story of how the tiniest ripples in reality might reveal the universe's deepest secrets. Buckle up, we're about to dive into the quantum foam. To picture the quantum foam, forget everything you know about space as an empty, silent void. Instead, imagine it like the surface of an ocean in a storm, constantly churning, bubbling with energy, where waves crash and swirl unpredictably. But here's the twist: this isn't happening across vast distances. This chaos unfolds at the smallest scales imaginable, so tiny that if you shrunk down to the size of a Planck length, a millionth of a billionth of a billionth of a centimeter, you'd see space-time itself flickering like static on an old TV screen. Where did this mind-bending idea come from? It all started when physicists tried to merge Einstein's theory of gravity with the bizarre rules of quantum mechanics. On their own, these theories work brilliantly. Einstein's equations describe the graceful dance of planets and galaxies, while quantum mechanics explains the frenzied behavior of particles. But when you try to combine them, the math breaks down, suggesting that space-time itself might not be continuous. Instead, it's stitched together from countless microscopic fluctuations, virtual particles that appear, vanish, and even form microscopic tunnels or black holes in the blink of an eye. We can't see these effects directly, but their echoes might be hidden in the way light travels across the universe or in the faint whispers of gravitational waves. What makes this so fascinating is that these fleeting disturbances could hold clues about the earliest moments of the cosmos. If space-time was born from this quantum turbulence, then studying the foam might reveal how the universe transitioned from pure chaos to the structured reality we know today. It's like uncovering the hidden blueprints of existence written in a language so subtle, we're only just beginning to decipher it. And while we may never witness quantum foam directly, the quest to understand it is pushing the boundaries of physics, forcing us to rethink what we thought was possible. Here's the next segment, flowing naturally from the previous discussion while introducing fresh angles and depth. Physics often progresses through moments of radical imagination, and few ideas were as bold as John Wheeler's vision of quantum foam. In the 1950s, while most scientists still pictured space as a smooth, unchanging stage, Wheeler dared to propose something far stranger. What if emptiness wasn't empty at all? His insight wasn't just poetic, it was a desperate attempt to bridge two warring titans of science: Einstein's elegant theory of gravity and the chaotic rules of quantum mechanics. The two frameworks refused to cooperate, and Wheeler realized the conflict might stem from a fundamental misunderstanding of space itself. His solution was as unsettling as it was brilliant. Instead of a static void, he envisioned space-time as a seething, dynamic ocean, where energy fluctuations erupted so violently that they could momentarily distort reality itself. Picture a pot of water on the verge of boiling, bubbles forming, bursting, and reforming in an endless dance. Now shrink that down to scales trillions of times smaller than an atom, and you've got quantum foam. These fleeting disturbances weren't just mathematical quirks. Wheeler argued they were the fingerprints of a deeper truth, where space and time lose their textbook perfection and become something wild and uncertain. The implications were staggering. If Wheeler was right, even a so-called vacuum brimmed with hidden energy, with particles and forces flickering in and out of existence too quickly to detect. This wasn't just theoretical musing. It helped explain why black holes could evaporate or why empty space might hold dark energy. Suddenly, the universe's most enigmatic phenomena had a potential hiding place in the froth beneath reality's surface. Today, Wheeler's intuition fuels cutting-edge research from string theory to loop quantum gravity. While we still lack direct proof of quantum foam, its fingerprints appear in the math governing everything from cosmic radiation to the behavior of black holes. His idea reshaped how physicists see the cosmos, turning empty space into one of science's most exciting frontiers. The quiet void, it seems, has never been quiet at all. But how can two of science's most successful theories, quantum mechanics and general relativity, be so violently at odds? Think of it like this. Quantum mechanics thrives in the realm of the absurdly small, where particles exist in multiple states at once, popping in and out of existence like cosmic fireflies. It's a world governed by chance, where uncertainty isn't a flaw in measurement but a fundamental law. Meanwhile, general relativity paints gravity as the elegant curvature of space-time, a smooth, predictable stage where massive objects bend its fabric like a bowling ball sinking into a trampoline. One theory thrives on probability, the other demands absolute certainty. When these two domains collide like near a black hole's singularity or in the first moments of the Big Bang, the equations explode into nonsense. Quantum mechanics insists space-time should be fractured, while relativity demands it remain unbroken. That's where quantum foam enters the picture, a proposed solution where space-time itself becomes grainy, fluctuating at the tiniest scales. Here, the smooth cosmic stage dissolves into a seething quantum storm, where miniature black holes might form and vanish in less than a trillionth of a second. This isn't just academic curiosity. Unifying these theories could answer existential questions like what sparked the Big Bang or whether time itself had a beginning. Some physicists suspect that hidden within the quantum foam's chaos lies a deeper structure, a hidden language that both quantum fields and gravity obey. String theory, loop quantum gravity, and other bold frameworks all chase this same dream, finding the common thread stitching reality together. For now, the quantum foam remains a tantalizing mystery. It defies direct observation, lurking just beyond our experimental reach, yet its fingerprints appear in the way particles scatter at high energies, or how empty space subtly crackles with untapped energy. Each clue brings us closer to deciphering the universe's greatest puzzle, not as two warring theories, but as a single, breathtaking story waiting to be told. Zooming in past atoms, past even the tiniest known particles, we arrive at a frontier where numbers lose meaning, the Planck scale. This isn't just small. This is the universe's ultimate limit of smallness, where a single centimeter divided by 10 followed by 34 zeros still wouldn't get you there. At this unimaginable scale, the smooth space-time we take for granted shatters into something far stranger. Picture a sheet of glass from a distance, perfectly flat, flawless. But get close enough and you see the cracks, the imperfections. The Planck scale is that magnifying glass for reality. Here, space isn't continuous. It's a storm of flickering fragments where microscopic black holes blink in and out of existence, and energy convulses in bursts so violent they warp the rules of cause and effect. These aren't just tiny versions of the physics we know. This is a realm where gravity and quantum mechanics fuse into something entirely new. Why does this matter? Because the Planck scale isn't just a curiosity, it's the operating system of the cosmos. The quantum foam churning here influences everything from how particles interact to the way the universe expanded in its first moments. Some theories suggest that if we could probe this scale, we might find evidence of extra dimensions or witness the atoms of space-time itself. But there's a catch. The energy needed to observe this realm is beyond anything our technology can muster. In fact, it's a quadrillion times more powerful than what the Large Hadron Collider can produce. That hasn't stopped physicists from searching for indirect clues. Some study the faint echoes of cosmic rays hitting Earth's atmosphere, hunting for minute delays that could betray space-time's grainy texture. Others analyze the light from distant quasars, looking for subtle distortions accumulated over billions of years. Each experiment is like trying to reconstruct a hurricane by studying the ripple it left in a pond. Daunting, but not impossible. What's clear is this: the Planck scale isn't just the domain of quantum foam, it's the canvas on which reality paints itself. The closer we get to understanding it, the closer we come to answering the oldest question of all. What is the universe really made of? Here's your engaging next segment, flowing naturally from the previous discussion while introducing fresh insights. At the heart of quantum foam's chaos lies one of nature's most peculiar tricks: virtual particles. These aren't just theoretical abstractions, they're fleeting guests in the universe, appearing and vanishing faster than thought itself. Imagine the vacuum of space not as emptiness, but as a stage where particles and their antiparticle counterparts perform an endless, invisible ballet, borrowing energy, dancing for a split second, then vanishing without a trace. This isn't magic, it's a direct consequence of quantum uncertainty, where even nothing seethes with potential. The rules of this dance are unlike anything in our everyday experience. Thanks to Heisenberg's uncertainty principle, the universe allows tiny energy loans, just enough for particle-antiparticle pairs to flicker into existence. These ghostly duets don't last long. They're forced to repay their energy debt almost instantly, annihilating each other in bursts of light or other quantum debris. But in that brief moment, they leave fingerprints on reality. Stack enough of these events together, and suddenly empty space isn't so empty, it's a boiling soup of quantum activity, where the foam's turbulence shapes the fabric of the cosmos itself. Remarkably, we've caught glimpses of these particles in action. Take the Casimir effect. Place two metal plates incredibly close together in a vacuum, and they're inexplicably pushed toward each other. Why? Because the narrow gap between them restricts the kinds of virtual particles that can form there, creating a pressure imbalance. Outside the plates, particles of all wavelengths pop in and out freely, but inside, only certain wavelengths fit. The result: the plates clink together as if nudged by unseen hands. It's like holding a book in a strong wind. The gusts you can't see still have undeniable force. Then there's Hawking radiation, where virtual particles near a black hole's edge become cosmic escape artists. Normally, particle pairs annihilate instantly. But at the event horizon, one might fall in while the other radiates away, stealing a tiny bit of the black hole's mass in the process. Over eons, this trickle of particles could evaporate even the mightiest black hole, a slow burn written in the language of quantum foam. What's stunning is that these ephemeral particles aren't just quirks of math. They're active players in the universe, shaping everything from the structure of atoms to the fate of stars. They remind us that reality at its core is restless, a place where nothing is an illusion, and every fragment of space thrums with hidden life. The quantum foam doesn't just host these ghosts, it's built by them. And in their brief, brilliant lives, we catch whispers of a deeper truth, that existence itself may be a story written in vanishing ink. If the quantum foam is a stormy ocean, then wormholes are its whirlpools, fleeting, chaotic, and vanishing as quickly as they form. At scales almost too small to comprehend, space-time might not just bubble with energy, it could be riddled with microscopic tunnels, stitching together distant points in an intricate, ever-changing web. These aren't the grand interstellar gateways of science fiction. They're barely whispers in the void, transient shortcuts that flicker into existence for fractions of a second before collapsing back into the foam's turbulent depths. Yet their very existence hints at something extraordinary, that the universe at its core might be threaded with hidden connections. The idea of wormholes isn't new. Einstein and physicist Nathan Rosen first toyed with the concept in the 1930s, uncovering solutions to general relativity that suggested bridges between distant regions of space-time. But while their Einstein-Rosen bridges were cosmic-scale structures, modern quantum gravity theories propose something far stranger, that these tunnels could be everywhere, woven into the fabric of reality at the tiniest scales. Imagine the quantum foam as a labyrinth of alleyways, each one a potential shortcut across space and time. Most are too unstable to traverse, snapping shut before anything could pass through. But their presence suggests a cosmos far more dynamic than we ever imagined. What gives these microscopic wormholes their fleeting existence? It all ties back to the same quantum uncertainty that allows virtual particles to borrow energy. In the foam's frenzy, space-time itself can twist into temporary tunnels, borrowing energy to stay open just long enough to leave a mark on the math. Some theories, like loop quantum gravity, even suggest these structures could be the atoms of space-time, tiny loops or knots that tangle and untangle to form the larger fabric of the universe. It's a radical vision, wormholes not as rare anomalies but as fundamental threads in the cosmic tapestry. The implications are staggering. If space-time is porous at the quantum level, could larger, stable wormholes exist? Could they connect distant galaxies or even different moments in time? The math doesn't rule it out, but there's a catch. Keeping a wormhole open long enough to traverse it would require something exotic, negative energy, or matter that defies gravity's pull. No one knows if such materials exist, but their theoretical possibility keeps the dream alive. Until then, the wormholes of the quantum foam remain elusive, glimpsed only in equations and thought experiments. Yet their ghostly presence nudges us toward a profound truth. The universe might not be a collection of isolated points, but a vast network of hidden pathways, a place where distance and separation are illusions, and the boundaries of reality are far softer than they seem. Whether we ever unlock their secrets, these tiny tunnels remind us that the cosmos is stranger, richer, and more interconnected than we dared to dream. Among the strangest ideas in modern physics is this: black holes might not just be cosmic giants lurking in the depths of space, they could also be microscopic, flickering in and out of existence like bubbles in a boiling pot. This isn't pure speculation, it's a direct consequence of throwing black holes into the quantum foam's chaotic playground. Picture space-time at the tiniest scales, not just as a seething sea of particles, but as a place where gravity itself goes haywire, crumpling into pinpricks of infinite density that vanish almost as quickly as they form. These aren't the supermassive monsters we're used to, they're quantum-scale black holes, so small and short-lived they challenge our very definition of reality. The math behind this is both elegant and unsettling. According to Hawking's groundbreaking work, black holes aren't eternal. They slowly leak energy, the famous Hawking radiation, and over incomprehensible stretches of time, they evaporate into nothingness. But in the quantum foam, this process gets turbocharged. Here, fluctuations in energy and space-time could spawn minuscule black holes that collapse almost instantly, their entire lifespan shorter than the blink of an eye. It's as if the fabric of space itself is riddled with microscopic scars, each one a black hole flickering into existence, radiating away its energy and disappearing without a trace. What's startling is how deeply this ties into the foam's behavior. Every time one of these micro-black holes forms and evaporates, it leaves a tiny imprint on space-time, a shudder in the quantum background. Some physicists suspect this could be the hidden engine behind the foam's turbulence, a dance of creation and destruction happening billions of times per second across every cubic centimeter of the universe. It's a dizzying thought. Empty space might be teeming with black holes we can't see, each one a whisper of gravity's wildest extremes. But why does this matter beyond theoretical curiosity? Because these fleeting black holes could hold clues to some of physics' biggest mysteries. If they exist, they'd be a laboratory for studying how gravity and quantum mechanics merge, a problem that stumped scientists for a century. Their evaporation might even leave behind subtle traces, like ripples in the cosmic microwave background or distortions in high-energy particle collisions. Catching these fingerprints would be like discovering a hidden layer of the universe, one where black holes aren't rare monsters but as commonplace as atoms. The quantum foam, then, isn't just a backdrop for reality. It's a crucible forging and erasing black holes in an endless cycle. Whether we ever detect them directly or not, their theoretical existence reshapes how we see the cosmos, not as a static stage, but as a dynamic, restless thing where even the darkest corners pulse with unseen life. And if we're right about this link, it means black holes from the tiniest to the titanic might all play by the same quantum rules, bound together in a web we're only beginning to untangle. Here's your next segment, crafted to flow naturally while introducing the Casimir effect with fresh energy and clarity. Sometimes the most profound truths reveal themselves in the quietest experiments. Take two smooth metal plates, place them parallel to each other in a perfect vacuum so close they're barely a hair's width apart, and something inexplicable happens. Despite no external force acting on them, the plates inch together as if pulled by an invisible hand. This isn't magic, it's the Casimir effect, one of the strangest and most consequential phenomena in quantum physics. What makes it revolutionary isn't just the tug between the plates, but what it implies. The quantum foam isn't just a wild theory, it leaves footprints in our reality. To grasp why this matters, we need to revisit virtual particles, those fleeting guests in the vacuum of space. Ordinarily, these particles flicker everywhere, forming and vanishing in a chaotic dance. But when you slide two plates impossibly close together, you're subtly changing the rules of that dance. The narrow gap between the plates becomes a sort of cosmic bottleneck. Only certain wavelengths of virtual particles can fit in that cramped space, while outside, particles of all sizes continue their frenetic performance. The result, more particles push inward on the plate's outer surfaces than press outward from within the gap. The imbalance creates a net force, a whisper-thin nudge that shouldn't exist if empty space were truly empty. First predicted by Dutch physicist Hendrik Casimir in 1948, this effect was long considered a quirky mathematical oddity. But in 1997, scientists at the University of Washington finally measured it with breathtaking precision. Their experiment confirmed what quantum theory had dared to suggest. The vacuum isn't passive. It crackles with latent energy, a seething backdrop to everything we see. The Casimir effect doesn't just hint at quantum foam, it shows us the foam's turbulence in action. Critically, this isn't just about two plates sticking together. The effect's implications ripple outward. If virtual particles can exert measurable forces, then the quantum foam's energy might influence everything from the stability of atoms to the expansion of the universe itself. Some researchers even speculate that manipulating Casimir forces could one day lead to breakthroughs in frictionless nanotechnology or exotic materials. But perhaps its greatest gift is simpler. It's a rare bridge between the abstract equations of quantum foam and the tangible world we can probe. the Casimir effect doesn't answer every question about the quantum vacuum. It doesn't, for instance, explain why the foam's energy doesn't curve the entire universe into a black hole, a puzzle still haunting cosmologists. But it does something equally vital. It grounds one of physics' wildest ideas in elegant, reproducible experiment. In the quiet tug of two metal plates, we find a message that reality's deepest layers, though hidden, are never truly silent. Here's your next segment, flowing naturally from the previous discussion while expanding on quantum gravity with fresh depth and energy. For over a century, physics has been split down the middle, like two brilliant minds speaking different languages. On one side, quantum mechanics paints reality as a probabilistic storm of particles, buzzing with uncertainty. On the other, Einstein's general relativity describes space-time as a smooth, bending fabric, warped by massive objects in perfect harmony. Both theories work flawlessly in their own domains, but clash violently when forced to meet. The result, a stalemate that's lasted generations. Yet hidden in this tension is a tantalizing possibility that both are fragments of a deeper, unified truth, one where quantum foam isn't just a quirk but a cornerstone. Enter quantum gravity, the grand quest to reconcile these warring frameworks. Imagine trying to stitch together two jigsaw puzzles from different boxes, where the pieces almost fit but not quite. That's the challenge physicists face. The leading contenders in this race, string theory, loop quantum gravity, and a handful of other bold ideas, all grapple with the same core question. How does space-time behave when you zoom in past atoms, past particles, down to the Planck scale's chaotic depths? String theory, for instance, rewrites the script entirely. It proposes that reality's fundamental building blocks aren't point-like particles but tiny, vibrating strings. Their oscillations create every force and particle we know, like musical notes emerging from a cosmic violin. In this framework, quantum foam might arise from strings twisting into intricate, higher-dimensional shapes, weaving space-time itself into existence. It's an elegant vision, but one that demands extra dimensions curled into spaces too small to see, a price not all physicists are willing to pay. Then there's loop quantum gravity, which takes a starkly different approach. Instead of smooth continuity, it suggests space-time is woven from indivisible atoms of volume tiny loops that link together like chainmail. Here, quantum foam isn't a turbulent sea but a dynamic network, where gaps between loops could allow wormholes or even explain the Big Bang's origin. Unlike string theory's extra dimensions, loops work squarely within our familiar four-dimensional world, offering a minimalist's answer to gravity's quantum enigma. Other frameworks like causal dynamical triangulation treat space-time as a mosaic of geometric blocks that constantly rearrange, a cosmic game of Tetris at the smallest scales. Each configuration represents a possible state of the universe, with quantum foam emerging from the churn. It's as if reality refreshes itself trillions of times per second, pixel by pixel. The stakes couldn't be higher. Unifying these theories wouldn't just tidy up the textbooks, it could rewrite them. A successful quantum gravity framework might finally explain what happened at time zero, the singularity before the Big Bang, or reveal whether black holes preserve information or erase it forever. It could even hint at whether time itself is fundamental or just an illusion emerging from deeper physics. For now, the hunt continues, fueled by equal parts math and imagination. Some clues might lie in the faint echoes of gravitational waves, or in lab experiments probing space-time's granularity. Others could emerge from pure theory, as physicists refine their equations in pursuit of an elusive aha moment. One thing's certain, the solution when it comes won't just describe quantum foam, it'll redefine reality itself, and that's a revolution worth waiting for. Imagine the universe's tiniest scales not as a storm of particles, but as an intricate symphony, one where every note is played by a vibrating string. This is the radical vision of string theory, where the quantum foam's chaos transforms into something far more structured. Instead of point-like particles popping in and out of existence, reality's fabric is woven from unimaginably small strings, each one oscillating at unique frequencies to produce every force and particle we know. In this framework, the foam's turbulence isn't random noise, it's the harmonics of a hidden melody. What makes this perspective so compelling is how elegantly it sidesteps the clashes between quantum mechanics and gravity. Strings don't just vibrate in the 3 dimensions we experience, they twist through higher dimensional spaces too subtle to detect. Picture a guitar string stretched across a table, its vibrations create familiar notes. But if the table were warped into unseen dimensions, those notes might soften or shift. Similarly, string theory suggests the foam's most violent fluctuations could smooth out in these extra dimensions, like waves dissolving into a calmer ocean. The chaos we perceive might just be a shadow of a far more ordered reality. Critics often point out the theory's biggest hurdle: we can't yet test it. These strings are thought to be trillions of times smaller than an atom's nucleus, and the energies needed to probe them dwarf anything our technology can muster. But mathematical consistency keeps the idea alive. String theory naturally incorporates gravity into the quantum world, a feat no other framework achieves so gracefully. It also hints at breathtaking possibilities, like the foam's microscopic knots forming bridges between dimensions or even birthing entire universes. Where does this leave the quantum foam? In string theory, it's no longer a turbulent sea but a dynamic lattice, where strings weave space-time itself. The foam's apparent randomness could simply be our limited view of a richer, multidimensional dance. While far from proven, this reimagining offers something invaluable, a path to unify physics' greatest contradictions. Whether strings are the final answer or just a stepping stone, they remind us that reality's deepest layers may be far stranger and more beautiful than we ever guessed. Here's the next segment of your script, crafted for seamless continuity and fresh engagement. While string theory adds hidden dimensions to the cosmic equation, loop quantum gravity takes a strikingly different path, one that reimagines space-time as a vast, shimmering web. Picture the universe not as a smooth continuum, but as a tapestry of interwoven threads, each one a tiny, indivisible loop of space itself. These loops don't just float passively, they link and tangle dynamically, their connections constantly shifting like an endless cosmic dance. Here, the quantum foam isn't chaos, it's the pulse of this living network, where space and time emerge stitch by stitch. This bold framework sidesteps the infinities that haunt other theories by embracing a radical idea: space-time isn't infinitely divisible. Just as matter is made of atoms, space itself might be built from finite grains, tiny parcels of volume woven together by these loops. At the Planck scale, the smooth geometry we're familiar with dissolves into a lattice of relationships where proximity and distance aren't fixed but fluid. A grain of space here might link directly to another far away, hinting at shortcuts akin to wormholes. It's as if the universe runs on a kind of quantum stitching, with the foam's turbulence reflecting the threads tightening or fraying at the smallest scales. What makes this approach so compelling is its mathematical elegance. Unlike string theory's extra dimensions, loop quantum gravity grounds itself firmly in the 4 dimensions we know, time included. The loop's interactions generate space-time's curvature naturally, bridging quantum mechanics and gravity without exotic add-ons. Even black holes transform in this view. Their singularities might dissolve into fuzzy knots of looped space, avoiding the infinite densities that break other theories. For physicists seeking a minimalist solution to unification, this is a breath of fresh air. Yet challenges remain. While the theory beautifully quantizes space, it struggles to explain how the large-scale smoothness of the cosmos emerges from this granularity, like stitching a silk sheet from rough yarn. Experiments to test its predictions, such as subtle shifts in high-energy light traversing the universe, remain tantalizingly out of reach, but the theory's promise keeps it alive. If space-time truly is a network, then every collision of particles, every warp of gravity, is just a ripple in the web's threads. Loop quantum gravity reminds us that reality might be more relational than substantial, a cosmic tapestry where connections define existence. Whether it's the final word on quantum foam or just a stepping stone, it reshapes our intuition. The universe isn't just in space and time. It is space and time woven one loop at a time. Here's your next segment, crafted to flow seamlessly while deepening the exploration of the holographic principle with fresh energy and clarity. What if everything we perceive, every galaxy, every atom, even the furious churn of quantum foam, is just a shadow of something happening on a distant, unimaginable surface? This isn't science fiction. It's the holographic principle, one of the most radical ideas in modern physics. Imagine standing in a room surrounded by mirrors where reflections stretch infinitely in every direction. Now take that concept and scale it up to the universe itself. The holographic principle suggests that all the information defining our three-dimensional reality might actually be encoded on a two-dimensional boundary far away, like a cosmic projector screen. The foam's turbulence, then, wouldn't be fundamental chaos. It could just be pixels flickering in a hologram, hinting at deeper laws we can't yet see. The roots of this idea trace back to an unexpected place, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, its hidden information, isn't proportional to its volume but to its surface area. In other words, everything inside could theoretically be mapped onto its event horizon like data on a hard drive. Years later, string theorists like Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might work the same way. If true, the quantum foam's apparent randomness isn't the full story. It's the universe's way of rendering complexity from simplicity, like a 3D movie emerging from a flat screen. How does this connect to the foam's frenetic energy? Think of it like a lake's surface during a storm. From above, the waves seem chaotic, unpredictable. But beneath, their motion is governed by orderly currents and pressures. Similarly, the holographic principle implies that the foam's turbulence might be the surface-level effect of more structured processes playing out in higher dimensions. What we perceive as virtual particles flickering in and out of existence could be projections, shadows cast by interactions happening somewhere else entirely. This wouldn't just tidy up quantum mechanics, it might finally reconcile it with gravity, since both could emerge from the same underlying code written on the universe's boundaries. Critics argue the principle is still speculative, a mathematical marvel lacking experimental proof. Yet clues are mounting. Certain models of quantum gravity naturally exhibit holographic properties, and experiments with ultra-cold quantum systems have shown behaviors eerily reminiscent of lower-dimensional projections. The AD-S/CFT correspondence, a landmark idea in string theory, even provides a concrete example of how a higher dimensional space can encode its physics on a lower dimensional boundary. It's as if the universe left breadcrumbs pointing toward its own blueprint. Whether the holographic principle holds or not, its allure is undeniable. It reframes reality as something stranger and more interconnected than we ever imagined, a place where the quantum foam storms might just be ripples on the surface of a deeper, quieter ocean. And if physicists are right, uncovering that ocean's rules could rewrite not just our understanding of space and time, but of existence itself. For now, the universe keeps its secrets close, etched in dimensions we're only beginning to glimpse. At the very beginning, before galaxies, before stars, before even light itself, there was a spark. Not in the sense of fire or explosion, but something far stranger, a quantum hiccup in the fabric of nothingness. Picture the universe in its first fleeting moments not as a void, but as a seething ocean of potential, where space and time flickered in and out of existence like static on a cosmic radio. In this primordial chaos, the tiniest ripples could have been the seeds of everything we know. This is where quantum foam meets the Big Bang. Inflation theory suggests that those microscopic fluctuations, those random twists and shudders in the foam, didn't just vanish. Instead, they were stretched, amplified, and frozen into the fabric of space-time as the universe expanded faster than light itself. Imagine blowing up a balloon with tiny dots drawn on its surface. As it inflates, those dots don't just grow, they warp, their imperfections magnified until they define the entire structure. In the same way, the universe's tiniest quantum jitters may have been stretched into vast cosmic wrinkles, the gravitational fingerprints that later sculpted galaxies, clusters, and the web-like architecture of the cosmos. What's astonishing is how precise this process had to be. Measurements of the cosmic microwave background, the afterglow of the Big Bang, reveal a pattern of temperature variations almost perfectly matching what quantum fluctuations would produce. It's as if we're staring at a fossilized echo of the foam's turbulence captured in the universe's first light. These ripples weren't random noise, they were the universe's first language, whispering the blueprint for all structure to come. But here's the deeper mystery. Why did these fluctuations exist at all? Some theories suggest they're inevitable, that even in a true vacuum, quantum uncertainty ensures space-time can never sit perfectly still. Others propose more exotic origins, like colliding bubble universes in a larger multiverse or remnants of a prior cosmic cycle. Whatever the cause, their legacy is undeniable. Without those primordial ripples, gravity would have had no variations to magnify, no seeds to nurture. The cosmos might have remained a featureless, lifeless expanse. This connection between quantum foam and cosmic structure isn't just academic, it's existential. It means the universe's grandest features, from the largest superclusters to the tiniest variations in the night sky, could trace back to events so small, so fleeting, they defy intuition. The foam isn't just a sideshow to reality. It might be the opening act of creation itself, and if we're right, studying its echoes could take us closer than ever to answering the ultimate question: how does something come from nothing? Deep in the void between galaxies, an unseen force is at work, pushing the universe apart faster and faster with each passing moment. Astronomers call this dark energy, but its true nature remains one of science's most baffling mysteries. What if the answer lies in the quantum foam's restless churn? Some physicists suspect that the same vacuum energy fueling those microscopic fluctuations might also be driving the cosmos to expand, a connection that could reshape our understanding of reality itself. Here's the puzzle. Quantum mechanics predicts that empty space should be brimming with energy, thanks to all those virtual particles flickering in and out of existence. If we could add up every fleeting burst in the quantum foam, the total should be unimaginably huge, enough to warp the universe beyond recognition. Yet when we measure dark energy's actual strength, it's staggeringly weaker than those calculations suggest. This mismatch, known as the cosmological constant problem, isn't just a small error. It's off by a factor of 1 followed by 120 zeros. That's like predicting a hurricane and finding only a whisper of breeze. So where does the discrepancy come from? Some theories suggest the foam's energy might partially cancel itself out, like waves crashing together to leave a deceptively calm surface. Others propose that extra dimensions or unknown symmetries could be suppressing its effects on cosmic scales. Then there's the wilder idea that dark energy isn't static at all. that it ebbs and flows as the quantum foam structure evolves over time. Imagine the universe's expansion as a tug of war between gravity's pull and the foam's push, with the balance shifting subtly across eons. While none of these explanations are proven, the pursuit itself is revolutionary. If the quantum foam really is tied to dark energy, it would mean the largest and smallest scales of reality are entangled in ways we're only beginning to grasp. Astronomers are already hunting for clues in the way distant supernovae brighten and fade, or how galaxy clusters drift apart over billions of years. Even the faintest ripple in the data could hint at foam's hidden influence. For now, the link remains speculative, a tantalizing what-if at the frontier of physics. But that's the thrill of science. Sometimes the deepest mysteries point not to dead ends but to doorways. Whether dark energy emerges from the quantum foam or something even stranger, one thing is certain: the universe still holds surprises we've yet to imagine. Physics has a way of humbling even the brightest minds, and nowhere is that more apparent than in the Vacuum Catastrophe, a mathematical meltdown that's been haunting theorists for nearly a century. At its heart lies a simple question: how much energy churns in the quantum foam? The answer should be straightforward. Plug the equations of quantum field theory into a calculator, sum up all those virtual particles flickering in the void, and voila! Except the result is a number so astronomically large it's laughable. Not just a little off, we're talking one followed by 120 zeros times stronger than what astronomers actually measure. It's like predicting a tsunami and finding only a ripple in a teacup. So what's going wrong? The trouble starts with the foam's relentless activity. Every cubic centimeter of empty space is a maelstrom of particle-antiparticle pairs borrowing energy, existing for mere instants, then vanishing back into the void. Individually, their impact is negligible, but add them all up across the infinite expanse of the universe, and the math suggests space should curve into a black hole under its own energy. Clearly, that hasn't happened. Our cosmos is remarkably flat, its expansion subtly accelerated by dark energy, not obliterated by it. This mismatch isn't just a gap in our knowledge, it's a canyon exposing flaws in our deepest theories. Some physicists suspect a cosmic sleight of hand. Perhaps the foam's positive and negative energy fluctuations almost cancel each other out, leaving behind the faint residue we call dark energy. Others propose wilder fixes, extra dimensions diluting the foam's strength, or undiscovered symmetries that suppress its effects. Then there's the radical notion that we're missing something fundamental, that space-time isn't just a backdrop for quantum fields, but an active participant with its own rules. Imagine the vacuum as a hall of mirrors where reflections conspire to hide most of the chaos, revealing only fragments to observers like us. The stakes couldn't be higher. Crack this puzzle and we might finally unify quantum mechanics and gravity, or stumble upon entirely new physics. Already, labs are testing ideas like variable dark energy or emergent gravity, while telescopes scour the cosmos for anomalies in the universe's expansion. Each clue narrows the possibilities, inching us toward a solution. But for now, the Vacuum Catastrophe stands as both a frustration and a beacon, proof that the quantum foam, for all its turbulence, is still holding its deepest secrets close. And that's what makes the hunt so thrilling. The hunt for quantum foam isn't just a theoretical puzzle, it's a high-stakes game of precision, pushing the boundaries of what science can measure. Think of it like trying to photograph a hummingbird's wings mid-flight with a telescope. The foam's fluctuations happen at scales a billion trillion times smaller than an atom and vanish in fractions of a femtosecond. But physicists refuse to let impossibility stand in their way. Instead, they're engineering experiments so sensitive they might catch whispers of the foam's chaos echoing across the cosmos. Take atomic clocks, for example. These aren't your average wall clocks, they're so precise they'd lose less than a second over the entire age of the universe. By comparing pairs of these ultra-accurate timekeepers, scientists hope to spot tiny discrepancies, fluctuations in the flow of time itself, that could betray space-time's grainy texture. If the foam is real, time might stutter imperceptibly at the smallest scales, like a film reel with missing frames. Similarly, gravitational wave detectors like LIGO could one day sense faint ripples not from colliding black holes, but from the foam's microscopic turbulence warping the detector's arms. Then there's the light from distant quasars traveling billions of years to reach us. Some models suggest the foam might scatter high-energy photons ever so slightly, like mist distorting a lighthouse beam. By analyzing these cosmic signals for anomalies, astronomers could uncover hints of space-time's hidden froth. Even more audacious are proposals to probe the foam using quantum entanglement, linking particles so their states remain mysteriously synchronized across vast distances. If the foam disrupts this connection in unexpected ways, it could reveal its presence indirectly. Of course, these experiments face staggering hurdles. The foam's signatures, if they exist, are buried under layers of cosmic noise and quantum uncertainty. Detecting them would require isolating a whisper in a hurricane. Yet the very attempt is revolutionary. Each experiment forces us to refine our tools, sharpen our theories, and question what we thought was measurable. Whether we succeed or fail, the pursuit itself is reshaping our understanding of reality's fabric, one impossibly precise observation at a time. This isn't just about proving a theory right or wrong. It's about testing the limits of human ingenuity, daring to ask, if space-time is imperfect, what else might we discover when we learn to see the universe in higher definition? The answers, when they come, won't just reveal the foam, they'll redefine the boundaries of the knowable. Quantum foam and the illusion of time. We think of time as the most reliable constant, an unwavering river flowing from past to future. But what if that's just an illusion? Beneath the surface of our everyday experience, time might not be smooth or continuous at all. Instead, it could emerge from the quantum foam's chaos, stuttering along in invisible, discrete steps so tiny they're almost impossible to fathom. Picture an old-fashioned film reel. When played at full speed, the motion looks fluid, seamless, but slow it down and you see the truth. It's actually a series of still frames flickering past. Time itself might work the same way. At the Planck scale where quantum foam reigns, the universe could be rendering reality in increments, like a cosmic projector advancing frame by frame. Each tick of this primordial clock would mark a fundamental unit of time, a Planck instant far too brief for any clock we've built to measure. This radical idea doesn't just tweak our understanding of time, it upends it. If time is granular, stitched together from fleeting quantum fluctuations, then the smooth progression we experience is a kind of cosmic sleight of hand. The foam's turbulence isn't background noise, it's the engine driving time forward. Some theories even suggest that causality, the unbreakable rule that cause precedes effect, might soften at these scales. In the foam's frenzy, microscopic reversals could momentarily defy our arrow of time, like eddies swirling backward in a stream. Why does this matter? Because if time emerges from something deeper, it could explain mysteries that have puzzled physicists for decades. For instance, why does time only move forward? The classical answer points to entropy, the universe's tendency toward disorder. But the quantum foam offers another layer, a microscopic landscape where time's direction isn't guaranteed but statistically favored. Over trillions of Planck-scale moments, the froth's chaos averages out into the steady march we perceive. It's like rolling dice. While any single toss is random, the law of large numbers ensures predictable outcomes. The implications stretch even further. If time is truly born from the foam, then black holes where gravity warps space-time to extremes might reveal its granular nature. Near a singularity, time could slow to a crawl or even fracture entirely, like a frozen film reel. Some models of loop quantum gravity hint that this breakdown might prevent singularities from forming at all, replacing them with a quantum bounce. Time wouldn't end, it would stutter, reset, and perhaps even reverse. Of course, proving any of this is staggeringly hard. Planck-scale time units are to a second what a second is to the age of the universe, orders of magnitude beyond our current tools. But scientists aren't giving up. Some are designing experiments to test time's smoothness using ultra-precise atomic clocks or quantum-entangled particles. Others scour the cosmos for clues in the light of distant gamma-ray bursts, hunting for signs that high-energy photons interact differently with space-time's granularity. What's clear is this: time isn't just the stage on which the universe unfolds. It might be the most profound illusion of all, a trick of the quantum foam's endless dance. And if that's true, then unraveling its secrets could bring us closer than ever to answering the grandest question: what is reality really? The quantum foam's hidden potential, a portal to infinite realities. What if our universe isn't the only one? What if the quantum foam, those flickering ripples at space-time's smallest scales, isn't just the canvas of our reality, but the loom weaving an endless tapestry of universes? This isn't wild speculation. It's the Multiverse Hypothesis, a daring extension of quantum theory that suggests the foam could be the birthplace of entire cosmos. Forget isolated bubbles floating in nothingness. Imagine the foam as a frothing sea of creation, where every turbulent surge might spawn a new universe, each with its own unique laws of physics. The idea builds on a startling possibility. Fluctuations in the quantum foam might not always vanish. Under the right conditions, they could inflate exponentially, stretching into self-contained realms entirely disconnected from our own. Think of it like boiling water. Most bubbles pop instantly, but some grow large enough to escape the pot. In this analogy, our universe is just one lucky bubble, while countless others may have formed with different properties. Some might harbor stronger gravity, others no stars at all. A handful could even harbor life, while the vast majority remain barren. How does this connect to the foam's chaos? The key lies in vacuum energy, the same seething potential that fuels virtual particles. If a fluctuation in the foam borrows enough energy and avoids repaying it too quickly, it could trigger a runaway expansion, birthing a new space-time bubble. Inflation theory, which explains our universe's rapid early growth, hints at this mechanism, but the multiverse takes it further. What if inflation isn't a one-time event, but an endless process, with universes budding eternally from the quantum substrate? Critics argue this is untestable, and they're not wrong. If other universes are forever beyond our cosmic horizon, how could we ever confirm their existence? Yet subtle clues might linger. Collisions between neighboring universes could leave imprints in the cosmic microwave background, like scars on ancient skin. Or perhaps the foam's generative power leaves statistical fingerprints in the distribution of galaxies. For now, these are just tantalizing maybes. What's undeniable is the paradigm shift this idea represents. The quantum foam isn't just a quirk of our universe's machinery. It might be the engine of reality itself, churning out worlds too strange for us to imagine. Whether the multiverse is real or not, it forces us to ask, if space-time can foam, warp, and spawn new realms, what other wonders hide in the fabric of the cosmos? The answer, like the foam, remains beautifully elusive. Quantum foam and consciousness. When physics meets the mind, there's a theory so bold, so speculative, it blurs the line between science and philosophy. What if the quantum foam isn't just the fabric of space-time, but also the hidden stage where consciousness and reality meet. The idea sounds like something ripped from a sci-fi novel, yet a handful of physicists and thinkers have dared to ask, could the mind itself play a role in the foam's chaotic dance? At first glance, the notion seems absurd. Consciousness belongs to biology, to the realm of neurons and synapses, not to Planck-scale fluctuations in the vacuum of space. But when you dive deeper, the connection isn't entirely baseless. Quantum mechanics already forces us to confront the observer effect, where the act of measurement appears to influence particles' behavior. Some interpretations, like the von Neumann-Wigner hypothesis, go further, suggesting that consciousness might be the ultimate collapser of quantum probabilities, turning fuzzy potentials into definite realities. Now take that idea and scale it down to the foam. If reality truly froths with uncertainty at its core, could the mind, through some poorly understood mechanism, interact with that turbulence? Proponents of this far-out theory argue that consciousness might not just observe the foam but subtly mold it, like a sculptor shaping clay. In this view, every thought, every perception could send ripples through space-time's deepest layers. Mainstream physics, of course, remains deeply skeptical. The brain operates at scales vastly larger than the Planck length, and no experiment has ever shown consciousness directly influencing quantum systems in a meaningful way. Yet the very fact that such theories exist speaks to the foam's mystique. It's a realm so bizarre, so fundamentally alien to our everyday experience, that it invites us to question everything, even the boundaries between thought and reality. Even if these ideas never hold up to scrutiny, they serve a purpose. They remind us that the quantum foam isn't just a problem for physicists. It's a challenge to our imagination, a cosmic Rorschach test that pushes us to consider whether reality is as fixed and impersonal as it seems, or whether, buried in its deepest layers, lies something far stranger. After all, if the foam can birth universes and warp time, who's to say where its surprises end? The quantum foam's existential whisper, rethinking reality itself for centuries, we've clung to the idea of a stable, orderly universe, a clockwork cosmos where laws govern every star, every atom with unshakable precision. But quantum foam shatters that illusion, revealing a far stranger truth. Beneath the surface, reality might be built on chaos. This isn't just a scientific revelation, it's a philosophical earthquake. If space-time seethes with randomness at its core, what does that mean for the certainties we take for granted? Are the laws of physics truly eternal, or are they more like ripples on a deeper, turbulent sea? Consider the implications. We've always assumed gravity, light, and quantum mechanics behave the same everywhere, eternal rules written into the fabric of existence. But if those rules emerge from the foam's churn, they might not be fixed at all. They could be local, even temporary, like patterns in a kaleidoscope, shifting as the universe evolves. Some theorists suggest that in the foam's deepest layers, causality itself might flicker, with effects briefly preceding causes or events unfolding in loops rather than lines. It's a vision that turns our most basic assumptions inside out. This uncertainty doesn't just challenge physics, it forces us to confront the limits of human understanding. Science thrives on predictability, on uncovering laws that hold true everywhere, always. Yet the foam whispers a humbling counterpoint. Perhaps our laws are just approximations, shadows cast by processes too alien for us to fully grasp. Imagine ants trying to map a hurricane. Their tiny scale would never capture the storm's true nature. In the same way, our tools and theories might only skim the surface of a reality far wilder than we've dared to imagine. But there's beauty in this mystery. The quantum foam doesn't just expose gaps in our knowledge, it redefines what knowledge is. Instead of a static set of answers, science becomes a living conversation with the cosmos, one where every discovery opens deeper questions. It invites us to wonder, if reality is this fluid at its foundation, what else might be possible? Could space-time itself one day be reshaped not by nature but by intelligence? The foam doesn't just describe the universe, it dares us to dream beyond it. For now, the questions outnumber the answers, but that's the thrill of the search. Whether the foam's chaos is the final word or just a stepping stone, it reminds us that the universe is richer, stranger, and more mysterious than we ever guessed. And in that uncertainty, there's something profoundly human, the audacity to keep questioning, even when the cosmos refuses to reply. Quantum foam in popular culture. When science fuels imagination, science fiction has always danced on the edge of reality, but few concepts blur that line as thrillingly as quantum foam. From blockbuster films to best-selling novels, this mind-bending idea has escaped the confines of physics papers and ignited the public's curiosity. Take Interstellar, where Matthew McConaughey's character plunges into a black hole, navigating a surreal, multi-dimensional labyrinth. While the movie takes artistic liberties, its portrayal of space-time as a mutable, chaotic fabric owes a debt to real theories about the foam's turbulent nature. It's not pure fantasy, it's science's wildest hypotheses amplified for the big screen. Carl Sagan once wrote that science is a collaborative enterprise spanning generations, but it's also a wellspring of wonder. In Cosmos, he wove cosmic ideas into poetic narratives, making abstract physics feel intimate and grand. Quantum foam, with its promise of hidden depths beneath reality's surface, fits perfectly into that tradition. It's no accident that documentaries and sci-fi alike return to this theme, using the foam as a metaphor for the universe's unfathomable complexity. Whether depicted as a shimmering quantum ocean or a crackling energy field, these portrayals share a common thread. The foam represents the frontier of the unknown. What's fascinating is how these creative takes shape public perception. Most viewers will never grapple with Planck-scale physics, but a gripping story can make the impossible feel tangible. When Doctor Who visualizes time as a wibbly-wobbly fabric, or the three-body problem describes protons unfolding into higher dimensions, they're borrowing the foam's essence. The idea that reality is stranger than it seems. Scientists might cringe at the oversimplifications, but these stories serve a vital role. They spark questions, fuel curiosity, and remind us that the universe is far more mysterious than our daily lives suggest. Yet there's a delicate balance at play. Pop culture often exaggerates or distorts the science, turning subtle theories into flashy plot devices. Wormholes become interstellar highways, quantum fluctuations morph into time travel loopholes. While physicists may nitpick the details, the broader impact is undeniable. These stories act as gateways, drawing audiences toward real science. A teenager watching Ant-Man shrink into the quantum realm might Google Planck length afterward. A viewer of Arrival might ponder how language shapes perception of time, a theme echoing the foam's challenge to classical physics. The foam's journey from equations to entertainment reveals something profound. Science and storytelling aren't opposites. They're partners in exploration. One relies on rigor, the other on metaphor, but both seek to answer the same awe-inspiring questions. Whether through a telescope or a film camera, humanity keeps peering into the void, searching for meaning in the chaos. And if quantum foam teaches us anything, it's that the answers, much like reality itself, may be richer and more tangled than we ever dreamed. Clearing the quantum confusion, what the foam really is, we've all seen those sci-fi visuals, space depicted as a bubbling, frothy sea like a cosmic cappuccino. But here's the truth, quantum foam isn't a literal substance you could scoop up in some futuristic net. It's not made of tiny bubbles or floating fragments. That word foam is just a metaphor, a poetic way to describe something far stranger. the unpredictable, probabilistic churn of space-time itself at the smallest scales imaginable. Think of it like static on an old radio. The noise isn't made of anything tangible, it's the result of invisible fluctuations in the signal. Similarly, the foam isn't a material or a structure. It's the mathematical fingerprint of space-time's inherent fuzziness, where the very concepts of here and now start to blur. At scales trillions of times smaller than an atom, the smooth stage of our universe dissolves into a storm of potentiality, where distances and durations flicker like candle flames in a breeze. This distinction matters because it keeps us grounded in science, not speculation. Some popular theories, especially those blending physics with metaphysics, treat the foam as if it were a tangible, almost magical substrate. But in reality, it's a framework, a way for physicists to grapple with the fact that space-time might not be continuous. Just as pixels make up a digital image, the foam could be the grain of reality, but even that's an oversimplification. There's no evidence it's built from discrete bits. It might simply behave that way under certain conditions. Why does this misconception persist? Partly because our brains crave concrete analogies. We're wired to picture the invisible in familiar terms, hence the soap bubble imagery. But the quantum realm defies intuition. For example, the foam's fluctuations don't mean space is boiling in the way water boils. Instead, they reflect the fundamental uncertainty baked into the universe, where energy and geometry can't be pinned down to a single, definite state. So when you hear phrases like "space is made of foam," remember, it's shorthand for something far subtler. The foam isn't a thing, it's a behavior, a property of reality at its most extreme. And understanding that distinction is the first step toward appreciating why this idea has captivated physicists for decades. It's not about finding some exotic material, it's about decoding the hidden language of existence itself. The next frontier, hunting for quantum foam's hidden patterns right now in labs around the world. Physicists are building tools that would have seemed like science fiction just a generation ago, machines designed to glimpse the universe at its most fundamental level. These aren't just incremental upgrades, they're radical leaps meant to probe the Planck scale, where quantum foam's turbulence defies conventional observation. Imagine trying to detect the wake of a single atom-sized boat in a stormy ocean. That's the scale of the challenge and the audacity of modern quantum foam research. At CERN, plans are already underway for the Future Circular Collider, a particle accelerator 4 times larger than the Large Hadron Collider. With energies approaching the exa-electron-volt range, it could reveal subtle distortions in particle collisions, hints that space-time itself has a grainy texture. Meanwhile, gravitational wave detectors like LISA, a space-based observatory set to launch in the 2030s, might catch whispers of microscopic black holes evaporating in the foam's depths. These projects don't just push engineering limits, they're hunting for anomalies that could rewrite physics textbooks, but brute force experiments aren't the only path forward. Quantum computers, with their ability to simulate systems too complex for classical machines, could model the foam's behavior in ways no lab ever could. By encoding quantum fluctuations into qubits, researchers might finally see how space-time emerges from chaos, like watching a city's traffic patterns crystallize from random individual movements. Early attempts are already hinting at unexpected structures in the foam's turbulence, suggesting order beneath the apparent randomness. The real game changer, though, could come from the cosmos itself. Ultra-high-energy cosmic rays particles hurled across the universe with energies 1,000,000 times beyond what our colliders can produce might bear scars from brushing against the foam's granularity. Telescopes like the Pierre Auger Observatory are sifting through these cosmic messengers for delays or distortions that betray space-time's hidden roughness. Even a single anomalous photon could tilt the scales toward a new paradigm. What makes this era so electrifying isn't just the technology, it's the growing sense that we're on the cusp of something transformative. The foam's mysteries have resisted scrutiny for decades, but the tools to crack them are finally taking shape. Whether through particle smashing, quantum algorithms, or cosmic eavesdropping, one thing is certain: the answers won't just illuminate the foam. They'll redefine how we see reality itself, and that's a revolution worth chasing. Quantum foam and the search for extraterrestrial life. We often imagine the ingredients for life as straightforward water, organic molecules, a stable planet orbiting the right kind of star. But what if there's an invisible player in this cosmic recipe? Hidden beneath the surface of our universe, quantum foam's chaotic churn might subtly shape the very conditions that allow life to emerge. It's a wild idea, one that bridges the tiniest scales of reality with the grandest questions we can ask. Are we alone, and how does life take root in the cosmos? At first glance, the connection seems tenuous. How could fluctuations in space-time's fabric events lasting mere fractions of a second influence something as tangible as a habitable planet? Yet consider this: the quantum foam's energy might leave fingerprints on the formation of stars and their planetary systems. During the fiery birth of a star, swirling clouds of gas and dust collapse under gravity, but minute quantum fluctuations could influence how matter clumps together. Over eons, these tiny ripples might determine whether a planetary system ends up with rocky worlds in the Goldilocks zone or a chaotic jumble of inhospitable giants. The foam's reach might extend even further. Some researchers speculate that its energy could play a role in the stability of complex molecules, the building blocks of life. On Earth, life relies on intricate chemical reactions where proteins fold, DNA replicates, and cells communicate with astonishing precision. If quantum foam introduces subtle instabilities at the molecular level, it might favor certain chemical pathways over others, gently nudging the universe toward complexity. Imagine the foam as a cosmic sieve, filtering out some possibilities while allowing others to flourish. Of course, this remains speculative. No experiment has ever linked quantum foam directly to biology, and mainstream astrobiology focuses on far more measurable factors like atmospheric composition or tidal forces. But the mere possibility invites us to think differently. If life isn't just a happy accident of chemistry but a phenomenon shaped by the universe's deepest layers, then our search for extraterrestrial life might need to broaden. Could we one day scan distant exoplanets not just for water or oxygen, but for signatures of quantum turbulence in their starlight? Skeptics rightly caution against overreaching. The foam's effects, if they exist, would be vanishingly slight, buried under the noise of more dominant forces. But history shows that breakthroughs often come from chasing improbable connections. The discovery of cosmic microwave background radiation, the echo of the Big Bang, was once dismissed as irrelevant, static. Today, it's a cornerstone of cosmology. Whether quantum foam shapes life or not, the exploration itself is transformative. It reminds us that the universe operates on scales both vast and infinitesimal, and that the threads connecting them might be woven tighter than we think. Every time we peer into the night sky, wondering if another world harbors life, we're also indirectly probing the quantum depths where the answers to our biggest questions could be hiding in the foam's fleeting dance. The hidden responsibility beneath reality's surface. Every scientific revolution comes with a dilemma. Not just can we push the boundaries of knowledge, but should we? Quantum foam research sits at this crossroads today. While the idea of manipulating space-time remains firmly in the realm of theory, the ethical implications are already sparking debate among physicists and philosophers alike. Imagine gaining the ability to tweak the fabric of reality itself, not just observing the foam's turbulence but sculpting it. The power to engineer wormholes, warp time, or even birth pocket universes sounds thrilling until you consider the unintended consequences. What if a microscopic experiment ripples outward, destabilizing the very structure of our cosmos? History offers sobering lessons here. When the first atomic bombs were detonated, scientists grappled with the terrifying realization that their work could alter the course of civilization. Quantum foam research doesn't carry the same immediate peril, but its long-term stakes might be just as profound. Unlike nuclear physics, where risks are confined to our planet, tampering with space-time's fundamental nature could have consequences we can't even model, effects that might span galaxies or epochs. Some theorists warn that certain manipulations could trigger vacuum decay, a catastrophic scenario where a bubble of true vacuum expands at light speed, rewriting the laws of physics in its wake. It's the ultimate what-if, one where a lab accident could, in theory, erase the universe as we know it. Yet the ethical questions extend beyond apocalyptic scenarios. Even preliminary research into quantum foam demands staggering resources, billions funneled into particle colliders, space telescopes, and quantum computers. In a world facing climate crises, poverty, and pandemics, should we prioritize probing Planck-scale physics? Defenders argue that foundational science has always yielded unexpected dividends. The same quantum mechanics that brought us uncertainty principles also gave us transistors and MRIs. Could understanding the foam unlock technologies we can't yet fathom: clean energy, disease eradication, or interstellar travel? Perhaps the biggest ethical challenge is one of accessibility. If humanity ever harnesses space-time manipulation, who controls it? Would it become the exclusive domain of superpowers and tech giants, or could it be governed equitably? The history of scientific advancement suggests a troubling pattern. Breakthroughs often widen the gap between privileged and marginalized communities. Quantum foam's potential applications, whether in communication, transportation, or energy, could either unite or fracture civilization further. For now, these discussions remain speculative. But they serve as a vital reminder: science doesn't exist in a moral vacuum. The quantum foam isn't just a puzzle to solve, it's a mirror reflecting our collective values. Do we charge ahead, driven by curiosity alone, or do we pause, weighing the costs of playing with reality's building blocks? The answers won't come from equations, they'll come from us. And that's a responsibility as vast as the universe itself. For centuries, scientific breakthroughs came from lone geniuses scribbling equations by candlelight, but the future of physics might look radically different. Picture an ultra-advanced AI combing through mountains of cosmic data, spotting patterns no human could ever detect, and whispering insights about quantum foam's deepest secrets. This isn't science fiction, it's already happening. Artificial intelligence is emerging as an indispensable partner in the hunt to decode reality's most elusive layer, and the implications are staggering. Take machine learning algorithms, for instance. These systems thrive on chaos, excelling at finding order in what looks like randomness. When trained on particle collision data or gravitational wave readings, they can flag anomalies that might hint at space-time's granular texture. Unlike traditional methods which rely on human-designed models, AI approaches the problem with fewer biases, free to uncover connections we haven't even thought to look for. It's like giving a microscope to someone who's only ever used a magnifying glass. The real game changer, though, lies in AI's potential to generate theories, not just test them. Current quantum gravity models, from string theory to loop quantum gravity, were painstakingly built over decades by teams of physicists. But what if an AI, trained on the full corpus of physics literature and experimental data, could propose entirely new frameworks overnight? Projects like Google's DeepMind are already dipping into this frontier, using neural networks to suggest novel solutions to long-standing problems in quantum mechanics. The day may come when an AI intuits a theory that perfectly unifies quantum foam with gravity, something humans have struggled with for a century. Skeptics argue that AI lacks the intuitive leaps of an Einstein or a Wheeler, that creativity can't be coded. Yet these systems don't need to think like humans, they just need to find paths we've missed. In 2022, researchers used AI to rediscover Newton's laws of motion purely from observational data, no prior physics knowledge required. If algorithms can reconstruct centuries-old breakthroughs from scratch, what might they uncover about Planck-scale physics? This partnership isn't without risks. Over-reliance on AI could lead science down blind alleys if the training data contains hidden flaws. And there's the existential question: if an AI solves quantum gravity, will we even understand how it reached its conclusion? But the potential rewards outweigh the fears. By augmenting human ingenuity with machine precision, we're not just accelerating discovery, we're redefining what's possible. The quantum foam has resisted traditional analysis for generations. Now, with AI as our collaborator, we might finally hear what it's been trying to tell us all along. Making quantum foam click: how we teach the universe's wildest idea, explaining quantum foam to a classroom full of students or anyone outside theoretical physics, is like trying to describe color to someone who's never seen light. The concepts are so far removed from everyday experience that traditional teaching methods often fall short. But here's the exciting part: the very strangeness of the foam makes it a perfect gateway to spark young minds. When a 12-year-old hears that space itself might be bubbling with invisible energy, their eyes light up with the same wonder that drove Einstein and Wheeler to rethink reality. That moment of curiosity, that's where the next scientific revolution begins. The key lies in creative translation, turning abstract math into vivid, relatable images. Take the cosmic popcorn analogy. Imagine space-time as a hot pan where kernels of virtual particles constantly pop into existence before vanishing again. It's not a perfect comparison. Real quantum foam doesn't involve literal popping, but it captures the foam's frenetic energy in a way equations alone can't. Other educators liken it to static on an old TV screen, where the flickering snow represents space-time's underlying graininess. These metaphors aren't just simplification, they're bridges helping students cross from confusion to aha. But analogies only go so far. To truly cement understanding, nothing beats hands-on exploration. Some classrooms simulate vacuum fluctuations with wave tanks, where rippling water models the foam's turbulent behavior. Others use tangled ropes or interconnected springs to demonstrate how space might be woven from dynamic loops. Even Minecraft has become an unlikely teaching tool, with virtual Planck-scale worlds built block by block to visualize quantum granularity. The goal isn't to replicate the foam's physics, that's impossible with macroscale tools, but to cultivate intuition. When a student manipulates a physical model, they're not just learning, they're experiencing the science. What makes this outreach vital isn't just the science itself, it's the mindset it fosters. Quantum foam defies classical intuition, forcing learners to embrace uncertainty and think in probabilities. A child who grapples with these ideas today might grow up to design experiments that finally probe the Planck scale or discover connections between quantum gravity and dark matter. And you don't need a lab coat to participate. Citizen science projects like distributed computing initiatives analyzing space-time data invite everyone to contribute to cutting-edge research. The takeaway: quantum foam isn't an exclusive club for PhDs. It's a shared frontier, a puzzle with pieces scattered across math, philosophy, and even art. Whether through a popcorn analogy, a makeshift wave tank, or a late-night stargazing session, every attempt to explain the foam plants seeds for future breakthroughs. Because the most important lesson we can teach isn't the answer, it's the courage to ask, what if? Quantum foam and the limits of human perception. Our brains evolved to navigate a world of trees, rivers, and predators, not a universe where space and time flicker like static on a screen. When we try to picture quantum foam, we're attempting to grasp something fundamentally alien to human experience. The scales involved are unimaginably small. If an atom were the size of a football stadium, the foam's turbulence would be happening on the blades of grass. It's no wonder our intuition fails us. Our senses simply weren't built to perceive reality at this level. Yet here's the paradox: even though we can't see, touch, or directly measure the quantum foam, we know it's there. How? Because the universe leaves clues. Think of it like tracking an invisible animal by its footprints. We might never glimpse the creature itself, but the disturbances it leaves behind, subtle shifts in particle behavior, anomalies in gravitational waves, tell us something real is moving beneath the surface. Mathematics acts as our night vision goggles, translating the imperceptible into equations that predict with stunning accuracy how the foam should influence the world we can observe. This rift between perception and reality isn't just a scientific challenge, it's a philosophical revelation. For centuries, we assumed that if something couldn't be seen or felt, it wasn't real. But quantum foam forces us to confront a deeper truth. Reality isn't limited to what our senses can detect. Just as a bat navigates the world through echolocation or a bee sees ultraviolet patterns on flowers, science equips us with tools to perceive the imperceptible. The foam isn't an abstraction, it's a layer of existence that operates by rules we're still deciphering. What's remarkable is how far this trust in indirect evidence has taken us. No one has ever seen an electron's orbit or the curvature of space-time, yet we build technologies based on their behavior every day. Quantum foam follows the same pattern. Its fingerprints appear in the way light travels across the cosmos, in the evaporation of black holes, even in the quantum jitters of particles held in lab traps. These aren't guesses, they're consistent, measurable effects that align with our models. Ultimately, the foam's elusiveness teaches us something profound about science itself. Progress doesn't always come from seeing more clearly. Sometimes it comes from learning to interpret differently. Whether through particle collisions, gravitational wave detectors, or the sheer predictive power of math, we're piecing together a reality that defies direct observation. And in doing so, we're rewriting not just our understanding of space and time, but the very definition of what it means to know something. The quantum foam might lie beyond our senses, but thanks to science, it's no longer beyond our grasp. The universe's hidden artistry. When science meets splendor, there's a quiet poetry woven into the fabric of reality, one that doesn't rely on stars or galaxies for its beauty, but on the invisible, frenetic dance of space-time itself. Quantum foam isn't just a scientific concept, it's a testament to the universe's boundless creativity. Imagine an artist who never lifts a brush, yet paints with energy and uncertainty, crafting a masterpiece at scales too small to see. This is the hidden artistry of the cosmos, a dynamic, ever-shifting canvas where emptiness is alive with potential. What makes this so captivating isn't just the physics, it's the sheer audacity of nature's design. The foam doesn't follow rigid rules like a clockwork mechanism. It thrives on spontaneity, with particles and forces flickering in and out of existence like fireflies in a summer night. These aren't flaws in reality's fabric, they're its most intricate stitches. Think of it like a symphony where the notes are constantly improvising, yet somehow, against all odds, creating harmony. The foam doesn't just exist, it performs a show unfolding trillions of times per second in every corner of the universe. There's a profound lesson here about how we perceive order and chaos. To our eyes, the night sky seems serene, a vast expanse of stillness. But beneath that calm lies a whirlwind of activity where space itself breathes and shudders. This duality, tranquility masking turbulence, mirrors the way great art often balances simplicity and complexity. A Mondrian painting with its clean lines hides meticulous calculation. A jazz solo, though spontaneous, follows deep-rooted patterns. Quantum foam, in its own way, is the universe's jazz, structured yet free, predictable in its unpredictability. Perhaps the most stirring part of this cosmic artistry is how it humbles and inspires us simultaneously. For all our telescopes and equations, we're still deciphering the foam's secrets, marveling at the questions it raises. Does space-time have a grain like a painter's canvas? Are there hidden symmetries guiding the chaos, like an unseen hand composing the storm? Every answer we uncover seems to reveal deeper layers of mystery, reminding us that the universe isn't just a puzzle to solve, it's a story to be savored, one fleeting fluctuation at a time. In the end, the foam's beauty lies in its refusal to be neatly categorized. It's science, yes, but also philosophy, art, and wonder rolled into one. It challenges us to see the universe not just as a collection of facts, but as a living, breathing work of genius, one that's been unfolding since the first moment of time, with or without an audience to witness it. And isn't that the most breathtaking idea of all? Quantum foam and the human quest for meaning since the dawn of civilization. We've looked to the stars, to myths, and to the invisible forces shaping our world, asking one persistent question: what is reality made of? Ancient cultures envisioned earth, air, fire, and water. Alchemists sought the philosopher's stone. Today, we probe the quantum foam, a frontier so small it defies imagination, yet so profound it reshapes how we see existence itself. This isn't just physics, it's the continuation of humanity's oldest conversation. What's striking is how little the core impulse has changed over millennia. The Babylonian astronomers mapping the heavens, the Greek philosophers debating atoms, and modern physicists simulating Planck-scale fluctuations are all driven by the same restless curiosity. Quantum foam might seem light years removed from myth, but it serves the same role, revealing order beneath chaos. Where ancestors saw gods shaping the world from primordial waters, we now see space-time flickering with virtual particles, different narratives, same yearning to decode the universe's blueprints. Yet there's a crucial difference. Earlier cosmologies offered certainty, placing humans at the center of a purposeful design. The foam, by contrast, confronts us with a universe that's fundamentally uncertain, where even the vacuum teems with anarchic energy. Rather than diminishing our significance, this revelation expands it. Every time we push the boundaries of knowledge, whether through telescopes or particle colliders, we're not just observers. We're participants in a grand, unfinished story, one where the act of questioning matters as much as the answers. Consider the parallels between ancient seers and modern scientists. Both use tools beyond ordinary perception, divination then, quantum equations now, to uncover hidden truths. Both face skepticism, yet persist because the search itself transforms us. The foam challenges our intuitions, yes, but also rewards us with something precious, a humbler, more awe-filled view of reality. It whispers that the universe is stranger than we dreamed, and that our journey to understand it is far from over. Perhaps the greatest gift of quantum foam isn't the science alone, but the way it rekindles childlike wonder. Staring into the night sky, a Neolithic hunter and a physicist today share the same gasp of amazement, one at the glitter of stars, the other at the knowledge that each point of light is tethered to a quantum sea beneath space itself. The questions evolve, but the awe remains, and in that shared wonder across time and cultures, we find something timeless, the unshakable human conviction that the universe is knowable, even when it dazzles us with its mysteries. This is why the foam matters beyond equations. It's not just about what space-time is, but what we are, a species forever reaching beyond the visible, daring to ask what lies beneath. And in that reaching, we honor every curious mind that ever gazed up and wondered. Quantum foam unmasked, separating science from speculation between the solid ground of established physics and the wild frontiers of speculation. Quantum foam often gets pulled into debates it never signed up for. You might have heard claims that this turbulent subatomic realm could unlock limitless free energy or allow us to bend reality like sci-fi telepaths. Here's the reality: while quantum foam is stranger than fiction, it's not a backdoor to magic. The genuine science behind it is rigorous, peer-reviewed, and far more interesting than the myths. Let's set the record straight. Quantum foam isn't some untapped power source waiting to be harnessed, those fleeting virtual particles flickering in the vacuum. They borrow energy so briefly that extracting usable power from them would violate the very laws of thermodynamics that make physics coherent in the first place. Think of it like trying to fuel a rocket with the static from a balloon. It might crackle impressively, but there's no sustainable energy there. The foam doesn't defy nature's rules, it obeys them in ways we're still deciphering. Then there's the idea that the foam could let us rewrite reality. Sure, its fluctuations suggest space-time isn't as static as it seems, but that doesn't mean we can reshape it at will. The foam's behavior is probabilistic, not programmable. You wouldn't confuse a dice roll with a rigged game, and the same logic applies here. The real wonder lies in how these random, infinitesimal events collectively give rise to the stable universe we experience. It's not about control, it's about understanding chaos that somehow averages into order. So why do these myths persist? Partly because the foam's counterintuitive nature leaves room for misinterpretation. When science says empty space isn't empty, it's easy for imagination to fill the gaps with grander, less grounded ideas. But physicists aren't dismissing the foam's weirdness, they're celebrating it within the bounds of evidence. From Hawking radiation to the Casimir effect, the foam's confirmed implications are jaw-dropping enough without resorting to embellishment. Here's the takeaway: quantum foam isn't a puzzle to solve for human advantage. It's a window into the universe's deepest workings, one that challenges us to think differently about space, time, and the very fabric of existence. And that journey, pursuing knowledge for its own sake with patience and integrity, is where the real magic of science happens. The foam's truths don't need hype, their power is in their precision. After all, isn't it more thrilling to explore a universe that surprises us without breaking its own rules? The unfinished symphony of quantum foam. There's something electric about standing at the edge of a scientific frontier, knowing that the next great leap could come from anywhere. The story of quantum foam isn't locked away in dusty textbooks or confined to elite labs. It's unfolding right now in the minds of students sketching equations on napkins, theorists chasing hunches in the dead of night, and international teams pooling data across continents. This isn't just physics, it's an open invitation to anyone daring enough to question, imagine, and persist. Take a moment to consider how many revolutions began with a single spark of curiosity. Einstein was a patent clerk when he reimagined space and time. Marie Curie's relentless experiments in a borrowed shed unveiled radioactivity. Today, the foam offers that same raw potential. A puzzle so profound it could rewrite the rules of reality, yet so unexplored that the key might lie in an idea no one's thought to test yet. Maybe it's a fresh analogy that cracks open the math, or an overlooked quirk in lab data that points to hidden dimensions. The breakthrough could even come from outside physics entirely, a biologist's insight into complexity, or a computer scientist's algorithm spotting patterns in chaos. What makes this moment so thrilling is the sheer diversity of tools at our disposal. A century ago, probing the Planck scale would have been pure fantasy. Now, we've got quantum computers simulating conditions no lab can recreate, AI uncovering links in mountains of cosmic data, and telescopes capturing whispers from the universe's first moments. Citizen science projects let amateurs sift through starlight for anomalies, while underground detectors hunt for particles that might carry clues from the foam's depths. The search has never been more collaborative or more open to unconventional thinkers. But here's the real magic: the foam doesn't discriminate. You don't need a Nobel Prize to wonder why particles flicker in a vacuum or to question if space-time's graininess affects how black holes age. Some of the most transformative ideas in science started as what-ifs scribbled on the margins of notebooks. The foam rewards bold questions, especially the ones that sound impossible at first. After all, every accepted truth was once considered heretical. So whether you're a researcher crunching equations, a student mesmerized by cosmic mysteries, or just someone who gazes up at the stars and wonders how, remember this: the next chapter in the foam's story hasn't been written yet. It's waiting for the right question, the fresh perspective, the stubborn refusal to accept "we don't know" as the final answer. And when that breakthrough comes, when someone finally pulls back the curtain on the foam's deepest secrets, it won't just change physics. It'll redefine what we thought was possible. The universe's greatest puzzles weren't meant to be solved by a single genius or era. They're a relay race across generations, each of us carrying the baton a little further. Quantum foam isn't just a subject to study, it's a conversation spanning centuries, and right now it's our turn to speak. So what will you add to the story? A farewell to the quantum frontier. Our voyage through the quantum foam has been anything but ordinary. We've wandered a realm where space and time lose their certainty, where the tiniest ripples might hold the blueprints of galaxies, and where emptiness itself crackles with hidden energy. From the birth pangs of the Big Bang to the evaporating whispers of black holes, this microscopic chaos has proven itself to be one of the universe's most astonishing architects. Yet for all we've uncovered, the foam remains a frontier. Its mysteries stretch beyond our current tools and theories, challenging us to refine our instruments and rethink our assumptions. Every unanswered question, whether about dark energy's origins or the true nature of time, isn't a dead end, but an invitation. Physics thrives on these open puzzles, each one a spark for the next generation of explorers. What's remarkable isn't just the science itself, but how it reshapes our perspective. The quantum foam teaches us that reality is far stranger and more interconnected than our senses suggest. The same turbulence that once birthed cosmic structures might one day reveal new layers of existence, extra dimensions, quantum gravity's elusive equation, or phenomena we haven't even named yet. This journey doesn't end here. With each experiment probing Planck-scale physics, every telescope scanning for anomalies in starlight, and every theorist daring to imagine beyond the known, we're inching closer to the foam's secrets. And you're part of this story too. Whether you're a seasoned science enthusiast or just dipping your toes into cosmic mysteries, curiosity is the compass that guides us all forward. So as we pause our exploration, remember, the universe's greatest wonders often lie just beyond the edge of understanding. If you've enjoyed unraveling this enigma with us, consider subscribing to dive deeper into science's boldest questions. Drop a comment below with your favorite revelation or the quantum puzzle you'd solve next. The conversation continues, and the cosmos never runs out of surprises. Until next time, keep looking up and down and into the invisible seams of reality itself. The adventure's just beginning.